For millions of students, a math classroom feels like a sterile void. Standardized education presents Cartesian translation as isolated formulas, disconnected from physical reality. But these exact mathematical vectors manifest directly in physical, indigenous realities. Stripping mathematics of its cultural origins creates a severe cognitive gap. Students are forced to memorize rote operations without understanding their tangible applications in the physical world. Ethnomathematics bypasses this disconnect by integrating indigenous knowledge systems directly into the formal curriculum. In West Africa, the Akan people of Ghana have spent centuries encoding advanced structural geometry into their daily lives and leadership. Artisans carve stencils from gourds, using precise mathematical calculation to place black dye patterns across grids, controlling the size, shape, and iteration of each design. These Adinkra designs are rigorous applications of transformational geometry and logarithmic scaling. By deconstructing these Akan artifacts, educators gain a first principles framework for teaching high-level STEM, moving sequentially from 2D coordinate planes to 3D volume measurement, and finally, computational programming. Understanding 2D geometry requires the ability to manipulate shapes accurately across a Cartesian plane. This 4-quadrant coordinate plane maps specific Adinkra symbols directly to the 4 core geometric transformations. The Funtun Funafu Denkyam Funafu, or twin crocodiles, symbol demonstrates reflection. It maintains exact mirror symmetry across both vertical and horizontal axes. In Twi, the mathematical term for reflection is Adane, or reversed image. Translation occurs when a base shape glides without altering orientation. The Ntisi Matemasi symbol copies itself by shifting a single circular node exactly along the x and y axes. The Twi term for this mathematical pull is Twe. Rotation dictates copying and spinning a shape around a fixed central point. The Encoding symbol builds its entire structure by iterating a single spiral arm exactly 90 degrees. In Twe, this rotation is entwaho, or spinning. Finally, dilation requires proportional scaling. The leaves of the Aya fern shrink by a specific mathematical percentage as they iterate up the central vertical axis. The Twi translation is ketoa for smaller and kesee for larger. Translating these abstract axioms into familiar linguistic and visual realities enables deep relational understanding. Students are defining structures they already recognize within their own culture. Adinkra designs frequently draw their structural inspiration from natural growth processes. Modeling biological growth, or morphogenesis, requires advanced nonlinear mathematics. This wireframe isolates the scaling factor between leaves. The identical curve governs the ram's horns and the Yin-Yame symbol. These curves align precisely with the Fibonacci sequence. Recursively subdividing a golden rectangle over the design traces a perfect logarithmic spiral. Akan artisans intuitively utilized logarithmic spirals to accurately represent morphogenesis. The advanced mathematics emerges as a natural byproduct of their deep cultural observation. This pedagogy extends beyond the 2D plane and into the 3D physical environment. Mensuration is the branch of mathematics dealing with the measurement of 3D objects, forming a critical focus of research at the Akenton Apia Menka University. Instead of a hypothetical cylinder, educators in the program use the waduro, a traditional wooden mortar found in typical Akan households. Replacing the abstract textbook drawing with a heavy physical tool fundamentally changes how students interact with the data. This 3D diagram shows students mapping the physical dimensions directly, measuring the vertical height and top radius. By unrolling the 3D form, students derive the surface area formula, 2 pi r squared plus 2 pi r h, from the actual measurements. Educators apply the same physical logic to the apayoa, a traditional clay earthenware bowl. This vector mapping illustrates how the thick rim of the molded clay provides a tangible model for calculating and differentiating inner and outer circumferences. Using utilitarian objects to map 3D mensuration anchors the formulas in the student's lived environment. The abstract physics becomes tangibly real. The final phase of this progressive curriculum takes analog cultural data and translates it into digital algorithmic logic. Software platforms like culturally situated design tools, or CSDTs, allow students to program these specific symbols. The process begins with manual data extraction. Students use protractors and graph paper to plot the physical coordinates, radii, and angles of the hand-carved stencils. Students input this extracted geometry into a visual block coding interface. A repeat loop instructs the software to shift the pen by a specific width, mimicking the Tway translation. Executing the code recursively generates a perfect digital reproduction of the Ntesi Mate Masi symbol. Indigenous design functions as an applied algorithm. By coding these symbols, students bridge the distance between ancient cultural heritage and modern computer science. We have tracked a complete scaffolding journey, starting at 2D coordinates, scaling through biological growth, extruding into 3D volume, and finishing in executable code. Throughout this process, cultural artifacts serve as mediating tools, successfully bypassing the cognitive disconnect caused by standard whiteboards. Research at the Akenton Apia Menpeg University shows that using these specific cultural symbols increases student performance across all 5 strands of mathematical proficiency, from conceptual understanding and strategic competence to adaptive reasoning. At the core of this data are the human artisans who encoded this mathematics centuries before modern software existed. Akan artisans have spent centuries refining a parallel mathematical framework,